The definition of continuity is that a function f has to be continuous as x equals c, which means that there is no interruption in the graph of f at c, which is your point. So we have three criteria that must be met in order to conclude continuity. The first rule is that the limit as x approaches 0 of your function must exist. So this means that the limit from the left, as x approaches 0 negative of your function, has to equal the limit from the right, as x approaches 0 positive of your function. And these both have to be equal to each other in order to be continuous. Our second criteria is that f of 0, which is your point, must exist. So your point must be in the domain. So let 0, it would be an example, would have to be in the domain of your function. And 3, your third criteria, is that f of 0 has to be equal to the limit of f as x approaches 0 of your function. This means that the limit from the left side and the right side has to equal your function. And some examples would be this one breaks our second rule, where f of 0 must exist. So our point must be in the domain, which this one means that is not defined because our point C is not in our domain because it's undefined. So this would break our second rule of our criteria, which would mean it's not continuous. Our third example, or second example, this one breaks our first rule, where the limit as x approaches 0 negative of the function has to equal limit of x approaches 0 positive of the function. Where this one, that our limit from the left, which is our a, does not equal the limit from the right, which is our b, and so they don't equal each other. So this breaks our first criteria. So this is considered not continuous. In our third example, breaks our third rule, where f of 0 has to equal limit as x approaches 0 of the function. So the limit from the left, which is the a, has to equal the function of c, and the limit from the right of b has to equal the function c, and they do not equal each other, which breaks the third rule, which makes it not continuous. Okay, so now we're going to talk about one-sided limits. The limit, so an example would be our right-handed limit. So the limit from the right, which is the right-handed limit, means that x approaches c from values greater than c. So since c would be our 0 on the graph, x is every single number, every positive number after c, which makes x a positive. So we can denote this as limit as x approaches c positive of our function equals L, and a graph would look like as L, which is all this, and our function f of x, the graph. So c, which is our 0, as x approaches every value to c, so this makes it positive, so c is less than x. And this is our right-handed limit because our graph comes from the right-hand side into the left hand, to the 0, which is c. And similarly, we have the left-hand limit, which is that x approaches c from values less than c. So since c's are 0, every value to the left of c is negative, so our c value will be greater and our x's are less. We denote this as limit as x approaches c negative of our function equals L. So we have the function now over on the left hand side, and now we have L, and we have our function, the graph. So x approaches the c values, so c is greater than x, because our c value is always greater than x, because the limit from L approaches the function of x, which makes this our left-hand limit. It's coming from the left side, as our x values would be negative and our c will be 0. So one-sided limits are useful in taking limits of functions involving radicals. So for instance, if n is an even integer, so if n equals 2, 4, 6, each of those numbers, so then the limit as x approaches 0 positive of n radical over x equals 0. And the one-sided limits are useful for problems like this because our radical will always give us a positive number, so it will always be a right-handed limit. Now we're going to do an example of a continuous or non-continuous function. So it gives us that f is continuous at x equals c, negative 3. It also gives us that f is continuous from the right at x equals 0. And it also gives us that f is discontinuous at x equals 2. So we put this on a graph, and we're going to put our number at 1. So we have our is continuous at negative 3. So at x equals negative 3, which right here is continuous, so it's a closed circle. And then at 2, it's not continuous, it's going to be an open circle. But no matter what, if we draw a graph, it will always go through our point that we chose, 1, which makes this continuous because it's continuous at our point 1. So if they were to tell us that is the graph continuous at x equals 1, it's yes, because it is. It's only continuous at negative 3 and discontinuous at 2. So no matter what, it will be continuous at 1. I'm done.
Question 2. Now show how to go about proving, disapproving continuity at A algebraically. That is, suppose you are given a function f. You want to know if f is continuous at A without pictures. What's the procedure? Explain it out. Be sure to give an example of a piecewise function also. For example, suppose f is a function. Is f continuous at 0? If so, why? If not, why not? First, we have to see if f of 0 is in the domain, and here we see that x equals 0 at 0. No, y is 0 at x equals 0. So it's in the domain. The next step is to set the limit of f of x as x approaches 0 from the left side equal to f of 0. Limit of f of x as x approaches 0 from the left is equal to the square root of 4 times 0 squared plus 1. Once this simplifies down, you get the square root of 1, and then that just equals 1. F of 0 is equal to 0, and then we see 1 does not equal 0. So we cannot continue because it's already not continuous.
This question asks us to find the value of A, knowing that f is continuous at x equals 2. knowing that f is continuous at 2 tells us three things. It tells us the limit as x approaches 2 from the right equals the limit as x approaches 2 from the left. That's 1. 2, f of 2 equals the right hand limit. And 3, f of 2 equals the left hand limit. I wrote that wrong. So starting with the left hand limit and the right hand limit equal to each other, I'm going to solve for a. So limit as x approaches 2 from the right equals one fourth a squared x squared plus 3. Plug in 2 for x, and then the limit as x approaches 2 from the left equals, let's see, looking back at the equation, or the question, ax squared, and then again plug in 2 for x. So now I can solve a by setting the right hand limit equal to the left hand limit. So I'm just going to move this over, so 1 fourth a squared is 4 plus 3 equal to the left hand limit for a. Then orders of operation says to multiply 1/4 by 4. So then I'll get 1a squared, which is just a squared, plus 3 equals 4a. I want everything on one side, so subtract 4 to the left. A squared minus 4a plus 3 equals 0. Then factor a, and minus 3, 1, then minus 3 is gonna get you, just checking, 4a. So a equals 1 and a equals 3. But a equals 1 and a equals 3 may not work for f of 2. So to see what works for f of 2, I have to set f of 2 equal to the left hand limit and the right hand limit. I'm going to start with setting it to the left hand limit. So just erase all this. So f of 2 equals limit as x approaches 2 from the left, f of 2 equals, looking back at the question, f of 2 equals a plus 9, and again limit as x approaches 2 from the left equals 1/4 a squared x squared plus 3, and then I plugged in 2 for x, and then I can set the function f of 2, which is that, equal to the left-hand limit, that. So, this was a plus 9 equals 1/4 a squared, let's make that 4, because 2 squared equals 4 plus 3. And now I can solve for a. Alright, so to solve for a in order of operations, 1/4 times 4 is 1, a squared, which is just a squared, plus 3 equals a plus 9. I'll move everything to the right side so the a squared doesn't become negative. So a squared minus a, then 3 minus 9 equals negative 6. And factor that to get a minus 3 and a plus 2. So a squared negative 6. So a equals 3, a equals negative 2. And before, when the limit of f of x, or the limit as x approached 2 from the positive equals the limit as x approached 2 from the negative, the values that made this true were a equals 3 and a equals 1. So the values I have for a right now are a equals 3, a equals 1, a equals 3, and a equals 2, negative 2. But if negative 2 were plugged into the limit from the right and the limit from the left, it would not make them equal to each other, so therefore not continuous. So that one goes away. And if 1 were plugged into f of 2 and the limit from the left hand, it would make them not equal to each other, so that goes away. So I'm left with a equals 3, which is what I got. A equals 3 when f of 2 are equal to, or set equal to the limit from the left, and when the left, and I got a equals 3 when the right hand limit and the left hand limit are equal to each other. So the answer is a equals 3, but just to check, I'm going to plug I'm going to set f of 2 equal to the right hand limit also. And I should get 3 as one of the answers for it. So f of 2 equals the limit x approaches 2 from the right. F of 2 again equals a plus 9, and the limit, or not equals but is, and the limit as x approaches 2 from the right is, let's see, ax squared, and then x2, or 2 gets plugged in for x. So then I set these equal to each other. So it was from before a plus 9 equals 4a. Subtract a, get 3a equals 9, divided by 3. A equals 3. So a makes the function continuous. Or when a is 3, the function is continuous.
Okay, so for number 4, the question states that suppose you have a function f given by f of x is equal to x to the 4th minus 1 over x minus 1, with x being less than 1, and 5x cubed minus 9x squared plus 7, with x being greater than or equal to 1. If f is f continuous at x equals 1? If so, why? If not, why not? So the first thing we need to do when we look at this function is we need to figure out if 1 is even in the domain, because if it isn't, then it already breaks one of the requirements, and if it doesn't satisfy all 3 requirements, then it automatically is not continuous. So the first thing I notice when I look at the function is I see that there's a x is greater than or equal to 1, meaning that x is equal to 1, so it's in the domain. Next, we must figure out if the limit from the left side equals the limit from the right side. To do this, we must plug in 1 for the limits coming from both sides. The reason we plug in 1 is because we're checking if x is continuous at 1, so we plug in 1. Let's start with the left side. So let's plug in 1. 1 to the 4th minus 1 over 1 minus 1. So 1 to the 4th is 1, 1 minus 1 is 0. We get 0 over 1 minus 1 equals 0, so we get left with 0 over 0. This is actually an indeterminate, and the reason it is because we can't say it's just 0 based off of the numerator, and we can't say it's undefined based off of the denominator, so it's kind of like both, but neither at the same time. So instead of, when we get a determinate, what we need to do is just more work, because we can't do anything with an indeterminate.
Factoring.
So to simplify this expression in a different way, we can always use the difference of square to factor the top. So x to the 4th can be factored into x squared minus 1 and x squared plus 1. This is the difference of squares. And then we have the denominator. Looking at this, you can factor it even more, because you see that there's an x squared minus 1 in the numerator, and that can factor even further. So we can write this as x plus 1, x minus 1, x squared plus 1, keeping the same denominator, x minus 1. Now that we factored it completely, you can notice that there's a special form of 1. X minus 1 over x minus 1 equals 1. So we can rewrite this as x plus 1 over x squared plus 1, because they cancel out. Now we can just take this in and plug in the same number we plugged in for the last one, which is 1, because we're trying to figure out if it's continuous at 1. So we'll just plug in 1, simplify that, we get 2 times 2, which gives us 4. So now we found out that the limit of the left side is 4, so we can move on to the right side. So the expression for the right side was 5x cubed minus 9x squared plus 7. Do the same thing, we have to plug in 1 because we're trying to see if it's continuous at 1. So 5 times 1 cubed minus 9 times 1 squared plus 7 simplifies to 5 times 1 minus 9 plus 7. You get 5 minus 9 plus 7, which is 3. Now that we found our limit from the left side and the limit from the right side, all we need to do is see if they're equal. So we found the limit of f of x approaching from the left side, and we have to see if it's equal to the limit of f of x as it's approaching right side. So for the left side we got 4, for the right side we got 3. 4 does not equal 3, therefore it does not satisfy the second requirement needed for it to be continuous. So the function is not continuous.